Hello, time for more astronomy. This time we're talking about distances to the stars and other stuff in the sky, celestial distances, and finally give you some idea of how we go about measuring those distances. So let's start out with some nice pictures. The top one there is a big cluster of stars called Messier 80, so the constellation Scorpius. And it's about 28,000 light years from Earth. So that's within our own galaxy. It's got a whole bunch of stars, including some that we term RR Lyra. But those objects are some things we use to measure distances. We'll talk more about those a little bit later. I'm going back in time a little bit. This image, well, this is a much more recent image, but the image is of the transit of Venus, meaning when we see Venus cross the face of the sun. And you can see the shadow of Venus in the upper right corner of this image, right? Like just as it got in front of the sun, or maybe just before it's leaving. I'm not sure. But even back in the 1800s, people were clever enough to realize that if you view the transit of Venus and time how long it takes from different latitudes on Earth, right? You're viewing it from different angles, there's actually sufficient information there to estimate the distance that the Earth is from Venus. Today though, if we want to know the distance to Venus, and the way that we do measure it rather precisely, is by using radar. So that technique of using radar works quite well when you're talking about solid objects that are within our solar system. So this is sort of the easy stuff. We're able to actually just generate radio waves. So that big antenna there is a radio wave generator and receiver. And the animation here shows a really simple illustration of how that radio, or how we use radio waves to find the distance to objects, right? This is what we call radar. So basically you generate some kind of radio wave and shoot it off towards the object you're interested in. It takes some time to travel along. When it encounters the object, it scatters off of it, and so all those radio waves that you send towards it scatter in all directions. Some of them come back to you, and from the ones that come back to you, they take a certain amount of time to come back, and overall the transit time for the radio wave to go out and then the one that bounced to come back can tell you the distance to that object, right? Because we know these waves are traveling at the speed of light. You know how fast something's going, how long it took to go a certain distance, and you can calculate that distance. If the objects aren't solid or don't in any way reflect radio waves, then that becomes a problem. Like the sun is just a big ball of gas, and so it doesn't really reflect radio waves that very well. Can't really measure the sun's distance this way. And the other thing is, once you get really far away, the radio waves that you send out become so weak by the time they have encountered the object and then some been reflected back, you just can't even detect them anymore, right? They've sort of died down enough where we won't ever detect the returning signal. This technique only really works for objects that are sort of within our solar system. Further out than that, there's just too weak of a signal. So the next sort of technique that we use, and we can do this for our planets too, but this allows us to look a little bit further out. It has to do with triangulation. So the triangulation is basically the process of viewing an object from two vantage points, and based on the shift in where that object is from those two vantage points, you can determine how far away it is, as long as you know the distance between those two vantage points. So in this image, you're trying to determine, say, the distance to a tree. And there's a river in between. You can't just walk out paces or lay down a tape measure or something, right? What you can do is observe the object from two different vantage points, A and B, and sort of measure the difference in angle between those two vantage points to that tree. So that sort of angle, that difference in vantage point, opening up here, along with the baseline, the distance between the 2 points you're observing from, gives us enough information to calculate how far that tree is. Right? It takes maybe a little bit of trigonometry. We're not actually going to calculate it, just saying that that's enough information, we can figure that out. It turns out that our brain does this process automatically, where it's evolved to do this using our two eyes. Right? So our two eyes, if you take an object like a pen and hold it up in front of you, and then close one eye, look at it, close the other eye, look at it, right? Switch back and forth, you see that in your field of vision, the object appears to be moving back and forth, right? So viewed from the left eye, it's to the one side, viewed from the right eye, it's moved over a little bit, right? And given the difference in that angle that you're viewing it from, and the fact that your eyes are spread apart, the baseline here is the distance between your eyes, right? Your brain puts that information together to tell you roughly how far away an object is. It does triangulation. The thing about this technique, though, is that for objects that are further and further away, you need a larger and larger baseline in order to detect the shift. So if an object gets really, really far away, then the difference between viewing it from over here and viewing it from over here is almost negligible, right? You can't even tell the difference. But if you view it from like over here, way over here, like two very spaced out vantage points, the baseline's really long, then you're going to see a noticeable difference in the angle, in the direction towards that object. So the baseline between your vantage points, the distance between your vantage points, is key in measuring further and further distances. That's why our eyes, only being spaced apart like a few inches, can only really do this within like a few dozen meters or so, or a few dozen yards, right? Like past maybe like 50, 60 yards, that change in the position of that object is not really making much of a difference between if I view it from the left eye or the right eye. And so the triangulation no longer works. Our brain uses other sources of information to determine how far away objects are at that point. So right, the baseline is key in making this sort of measurement. Something else that's key that might not be obvious is that you need some sort of backdrop that's far beyond the object you're trying to view. Right? Because in order to say that that object looks like it's at a different angle or has a different direction from my different viewpoints, I need to somehow situate that object within some like background area. Right? So like in the picture on the left there, I did this sort of two pictures of a pen from left and right eye, and I just sort of drew a really simple little like grid of dots. Right? So you could tell from one side the pen is on to the right a little bit, from the other side the pen's to the left. In this triangulation, you're using like the mountains in the far background. Because if it's just sort of blank behind the thing and there's nothing behind that, then there's no way to really tell how the angle had changed from one vantage point to the other. Right? So you need this sort of background. Another way to describe this technique is sometimes called parallax. Though parallax, the term is used in a number of different areas. Like you could talk about the technique of viewing things from different angles as parallax. Also, the angle that is the difference when you view from those different vantage points, that's the parallax angle, or that is parallax too. So it's a little bit confusing. But this is still the triangulation process. I just drew a diagram on the left, pretty much of what the picture is when we're trying to triangulate the tree, and indicating the angle between the two directions. So like from A viewing C, and then from B viewing C, that is the difference in the direction between the two vantage points. Okay? And we can quantify that as an angle. Again, that angle we sometimes call parallax. I think technically the parallax is half that angle for not obvious reasons, but we could essentially just think of that angle, right? It's that difference in direction from the two vantage points. And yeah, as I pointed out, I don't know if I mentioned this actually already, but the further away an object is, the smaller that angle becomes, the smaller the difference is between the viewing from vantage point A and B. Okay? And if it's a much smaller angle, it's a much smaller difference when viewed from the two vantage points, it becomes more and more difficult to distinguish that there even is a difference. Okay? So once you get to really far, far away objects, the same baseline doesn't do as well anymore. Meaning that you need to try to get a bigger baseline. Further and further away, you kind of need to keep expanding your baseline in order to still be able to detect a change in those vantage points. But if you can't detect that change, and you know the distance between A and B, the baseline there, then we can calculate the distance to the object. Something that people realized a while ago is that one of the biggest baselines we could easily use is the difference between Earth on one side of its orbit and on the other side of its orbit, about 2 AU. This image here then is showing that same sort of triangulation process, but we're now thinking of the Earth being on one side of the Sun, or one part of its orbit, as one vantage point. We're going to view some star far away. So we view it from A, one side of the orbit, and then all the way until we get over to B, view that same star again from the other side of the orbit. And that way the baseline is sort of the diagonal, or is the diameter of that orbit. It's almost a circle, so it's like a diameter. Right? But it's about 2 astronomical units. I'm struggling to remember how far it is right now. Also in this image, right, we see the object, and then the viewing sort of directions from A and from B continue on onto these sort of far stars. Because if we imagine what it looks like to view this object from vantage point A, right, the object's little red dot, from vantage point A, that star looks like it's in this position relative to the other stars that are much further away. So then when we view it from the other side of Earth's orbit, right, point B, that star is now shifted down relative to those very far stars. So given the difference between those two pictures, we can determine that angle between those two vantage points, and then again of that along with the baseline, which is now 2 astronomical units, can tell us the distance to that star. So yeah, as shown in there, technically the parallax angle is just half of that angle, but for our purposes, it doesn't really matter. However, the way we measure that angle is usually in something called arc seconds, which I've told you about before, I think probably a while back. But 1 arc second is 1/3600th of a degree. Very, very small. I used this example before too, but if you want to imagine an arc second, what 1 arc second looks like, you have to imagine a quarter that you're viewing from about 3 miles away. Really tiny. So, yeah. This image is definitely not to scale, because even if we're looking at like the nearest star to us, which is in like Alpha Centauri, for that star system, the parallax angle is only 1.5 arc seconds. Still about 1/3600th of a degree. Right? That angle is teeny tiny. But with some very good telescopes, we're able to measure a change that small from one side of Earth's orbit to the other. We can see that tiny little shift in the stars that are nearby us at least. This technique has a range, and it only gets us sort of like within our stellar neighborhood, right? Not across the galaxy, and definitely not outside the galaxy. Yeah, the book mentions an interesting note where people tried to do this technique for measuring the distance to stars before they had telescopes, or at least anywhere near decent telescopes, and they weren't able to detect any change in direction to a star, even using Earth's orbit as the baseline. So on that basis, some people seem to have reverted to the idea that the Earth doesn't actually orbit the Sun. So if it did, we should see some shift in the vantage points towards the stars. The only takeaway there is a lack of imagination, specifically in how far away stars are. Right? They didn't imagine that stars could be so far away that even looking from opposite sides of Earth orbit, we couldn't see a shift in them with our eyes. Even the nearest stars are very far. I mentioned before, there's this thing called the parsec, which is also a unit of distance that's used in astronomy. Again, I'm going to try to stick to light years. I think it's more useful for our purposes at least, but at least wanted to tell you what the parsec is. Basically, it's a contraction or combination of the words parallax and arc second. It turns out that a parsec is 1 arc second of parallax when you're using Earth's orbit as the baseline. And again, that change in direction, the parallax, depends on how wide the baseline is. So if we use just like the Earth's diameter, you viewed a star from one side of the Earth to the other side of the Earth, much shorter baseline, meaning the parallax that you would get to an object is much smaller than you would if you used the Earth's whole orbit as the baseline. If you do use 1 arc second and Earth's baseline, turns out that is about 3.3 light years, which is 200,000 astronomical units, or about 30 trillion kilometers. It's quite far, right? And that's just what we define as a parsec. So a light year is about a third of a parsec. So shown here in the bottom right is a comparison of sort of the old limit to this technique and the new limit. So the old limit, I think, was set by some satellite or space-based observatory, Hipparchus. But it's limited, I think, partly by its orbit, but also just partly by the ability of the technology. Right? So you can get a bigger and bigger baseline, sure, but if you can also get telescopes that can resolve smaller and smaller dots, that helps you too in being able to distinguish a slight shift, right? Because if a dot in your image is like this big, right, but the star's like right in there, the star is just one dot, but you can't resolve that very well, so you end up with this kind of blurry area. Right? And if there's a tiny little shift in that, it's very hard to detect. Right? But if your technology gets better, then you can shrink down the size of that dot in your image, and you can actually then detect smaller shifts. So that was the old sort of limit and shown relative to our galaxy, Milky Way galaxy. The new limit supposedly is being set by this new orbital observatory called Gaia. And it's a picture of it up on the left there. So Gaia is doing this whole survey and using Parallax to make like a 3D map of our whole stellar neighborhood. It's still limited. It gets us about 30,000 light years out, which is about a third the width of the galaxy. So that's pretty darn far away from us, but in terms of the universe, that's just our little local spot. We need other techniques that might be able to get us even further out. So one of those things has to do with variable stars. So if we look out into the universe, we see a number of stars that vary in how bright they are over time. Right? And they can vary in a number of different ways. One particular way that's useful, or one particular kind of star that varies, that we found to be very useful, is one that gets brighter and dimmer in a periodic way. I mean, it sort of repeats the same, like, pulsing pattern. So we call these pulsating variable stars. And some of the two biggest categories are Cepheid, we call Cepheid variable stars, and the RR Lyrae. Lyrae? I don't know how to say that. But yeah, another type of variable star. The image here is actually of a variable star. It was taken multiple images by the Hubble telescope, and it is a Cepheid variable that is in the Andromeda galaxy. And so you can see as the time advances, the star gets brighter, dimmer, brighter, dimmer, and it does this in a very nice repeating way. If you were to graph the brightness of the star over time, you get what's called a light curve, and it will look something like this for our pulsating variable stars. Like start on the far left there, the light has been dimming, and it's dimmed a bit more, and then right around 2 days into your measuring, it starts to brighten up, and then right around three-ish days, it starts to fall down again. Right? It keeps falling down until about 7 days into your measuring, and then it starts to brighten up again. Then it falls down, then it brightens up, then it falls down. Right? This is a repeating sort of pulsing pattern. Probably useful to note now that this varying is not the kind of varying that you see normally when you look out at stars. You see them like twinkle. Right? It seems like they get dimmer and brighter, dimmer and brighter. That, as I've told you before, has to do with the atmosphere interfering with the light coming towards us. Right? The atmosphere, when it's really turbulent, acts like a lens, or like a bunch of different lenses throughout the sky, and so the light gets kind of refracted and bent around, and not all of it always makes it to you, so it looks like the star gets dimmer and brighter. That is not this, right? These are the stars themselves are actually getting dimmer and brighter in this repeating pattern. Some broad things about these stars, the Cepheids, they range in sort of like how dim and how bright they get. Like that change could be a few percent of its total brightness, its total luminosity, all the way up to like 1,000%. Like 100 times it can vary in how bright and dim it gets. The period, or the time it takes to repeat this pulse, is anywhere from like days to months. The other type, the RR Lyra, I don't know, I think I've said that different every time. I don't know. But their brightness really only varies by about 200%, like 2 times its luminosity. And the periods are generally about a day or less. There are other types of these variable stars. These are just the ones we're going to look at, and some of the most important categories in general. But there's all these other ones too. And there's even subcategories of these Cepheid and Lyra ones. We're just going to talk a little bit more about the Cepheid ones. So one place that we discovered or first noticed a bunch of the Cepheid variables is in the Large Magellanic Cloud, which is sort of like a satellite galaxy to ours. The illustration on the left is of our galaxy, the Milky Way. So we're in that swirling pinwheel looking thing. And these sort of satellite galaxies, one the Large Magellanic Cloud, shown there. There's also a small Magellanic Cloud. Similar sort of galaxy like the other one, just a bit smaller. Still sort of this like satellite around our galaxy. Just to give you an idea, like the relative sort of sizes and distances there. This cloud, or these clouds, are outside of our galaxy, but relatively speaking to like intergalactic distances, they're pretty close. They're in our galactic neighborhood, you might say. The Large Magellanic Cloud is actually about 160,000 light years away from us. And something that's pretty nice is that it's not like terribly enormous in size, and it's quite far away. So when we view the stars in that cloud, they're like almost roughly at the same distance from us. So the book gives an example of this where, like, you know, if I were in LA, then like all of the suburbs of LA can seem far away from each other, or they're a good distance away from each other. But if I'm thinking about like how far away I am from all those suburbs when I'm in New York, all the way on the other side of the country, all those suburbs are basically in the same distance from me. The fact that they're actually not exactly the same almost doesn't matter, right? Relative to how large the distance is from the Milky Way to the Large Magellanic Cloud, a lot of those stars are basically at the same distance, 160,000 light years. Which is really nice because it allowed us to sort of study these Cepheid variable stars, a bunch of different ones in that cloud that are all roughly at the same distance. So we could try to tease out other information, given that we already knew not necessarily how far away they were, but we knew that they're all about the same distance. So any other variations in how they looked wasn't going to depend on the distance, right? They're all right around the same distance. What was found out by looking at a bunch of those Cepheids at roughly the same distance was that their brightness, or their luminosity, is directly related to the time that they take to go through a pulse. A more precise way of saying that is that their luminosity is proportional to their period. But if we bring back that light curve from before and look at like how long does it take to go through a full cycle, the period of that pulsing, for that particular light curve, it looks like about 5.5 days. The fact that the Cepheid's luminosity is proportional to their period means that if we looked at a different Cepheid and it had, say, like a period of 10 days, or maybe 11 days, it was twice the period of that one, then its luminosity, we could say, is twice the luminosity of this first one. The period doubled, the luminosity doubled. Alright, I also wanted to mention that what is going on with these stars to make them pulse like that, it seems to be that these are sort of regular stars, like main sequence stars, that have gotten close to the end of their life, meaning that they burn through most of the protons that were available, so there's almost no protons to keep going in that proton-proton fusion, and they're sort of sputtering, convulsing, right? So they want to keep burning through stuff, right? There's a lot of gravitational energy is crushing down, keeps increasing the temperature, but they're almost out of stuff. It's almost like a car that's running out of gas. It starts to like sputter. And that sort of sputtering or convulsing, for the star then, it means that that star is like actually in size is expanding and contracting. And that's affecting its luminosity. It's going up and down and up and down. So this is all very well and good, but knowing that luminosity is proportional to period doesn't actually tell us the actual luminosity of any of these stars, right? It's sort of like we know the slope of a line, but we don't have any gauge of like where it actually lies vertically, right? It could be down here, it could be up here, right? We know that there's this relationship, but I don't actually know how, sort of where it starts. In order to know that, we need some way to calibrate for the luminosity of these stars. Right? Calibrating is maybe a tricky idea, so I think we're going to talk about calibration for just a minute. So I came up with this maybe silly example where you want to measure, say, the distance to different objects in your room from, like the doorway into your room. You want to do that, but you don't have any sort of standard measuring tools, your ruler, measuring tape, meter stick. You just don't happen to have any of those things, so you decide, I still want to take measurements of some kind, and then later I can just relate those to our sort of standard, and then things will work out all right. So if you don't have any of those tools, well, you just take something that has length, and then start measuring all these distances in units of that length. Right? So say you take a pencil, right, and you're measuring the distance from the door to like the chair, one of the chairs in your room, with pencil lengths. Turns out maybe the chair is 37 pencil lengths from the door. You measure, say, to the bed 13 and a half pencil lengths from the door. So you're measuring the distance to all these different things, but you haven't really calibrated your system, right? We don't know how to actually express that in any sort of normal units that other people would use, and so that we could all kind of share. Right? How would you calibrate these measurements? Well, you need to actually, at some point, figure out how long your pencil is. Right? Because all your measurements are done in pencil length. So if we know the length of your pencil, we can convert all those measurements into, say, like meters. If you did that, maybe you go and you measure your pencil length, and it's a tenth of a meter. That long. Now that I do that, I can convert my pencil lengths into a sort of standard unit. Turns out the chair is 3.7 meters from the door. The bed, 1.35 meters from the door. So I'm using my pencil as a measuring device, and I can tell the relationship between things with that unit of measurement, right? Like 37 pencil lengths is 2.5, 3 times the distance from to the bed, right? I can know those relationships, but to know the absolute lengths, I need to calibrate this by measuring the length of my pencil. So back to thinking then about these pulsing stars, we know that their luminosity is proportional to their period, but we need to sort of calibrate for a base luminosity. Just a little animation here of like, almost cartoonish, some stars in a star field, and there's a couple of pulsing variable stars in there. That might be something we can look at. So how do we go about calibrating for these luminosities? Well, it's not that easy. It's kind of tricky. But tried to put it sort of simply here in this 4-step process, right? So in order to calibrate, we'll start by going back to Parallax and finding the distance to some nearby stars, right? And using the distance that they are away from us and their apparent brightness, how bright they seem to us, we can calculate their actual luminosities, how much energy they're actually putting out. We do that for a bunch of different stars that are near enough for us to use parallax, and we place those all on the HR diagram, or on an HR diagram. So you remember that diagram related temperature and luminosity of stars. Then we're able to sort of figure out the actual luminosities of stars based on their temperature. Right? Another way to say that is their spectral class. Sort of realizing that buried in here is another calibration, which is the HR diagram. And we're going to come back to that, I think, in just a slide or two. But anyway, assuming we do that so that we can relate the star's temperature to its luminosity, then we go back to looking out further around these sort of variable stars, so like back out to the Large Magellanic Cloud, and look at other stars around those that fall nicely on our HR diagram, right? We can measure their temperature, which from the HR diagram would give us their luminosity, tell us how much energy they're actually putting that out. And then if you ever have the actual luminosity of a star, then that, along with its apparent brightness, how bright it looks to us, we can measure its distance, we can calculate its distance. So then finally we would have the distance to stars that are very near those pulsing variable stars. So then we can say we have the distance basically to those variable stars, and given their distance and how bright they appear to us, their apparent brightness, we can calculate their actual luminosity. So not only now do we know that the luminosity is proportional to the period, we've actually calibrated it so we can say, given a period, I can tell you the luminosity of that star. It's a very powerful thing. You can look out at the night sky and essentially, if you find one of these Cepheid stars in a very distant area and you can measure its period, then you can calculate its luminosity. And if you can calculate its luminosity, then the only other thing you really need is just measuring how bright it appears to us, its apparent brightness. The luminosity, along with the apparent brightness, can give us its distance. Remind you maybe why that's the case with this image that I presented, I don't know, earlier on in the course, but this ability to relate luminosity, apparent brightness, and distance comes from this thing called the inverse square law, where very simply it says that as this sort of energy spreads out, its intensity falls off as the square of the distance it moved away. So in the image, if we think about like 1 unit away from this star, then there's this particular block of energy. There's this amount of energy that falls on that little square, 1 unit, I don't know, 1 astronomical unit maybe away from that star. If you go to 2 astronomical units away, then the energy that was hitting that 1 square has spread out to 4 squares. Right? You went twice as far away, the energy gets spread out over 4 times the area, meaning that the intensity at any point there is dropped down by a factor of 4. You move 3 times as far away, that same energy is now spread over 9 times the area. The intensity would fall off by that factor of 9. So if you know how much energy is being put out from the source, and you measure the energy that's actually making it to you, the inverse square law allows us to calculate the distance that you are away from that object. And this is simply a fact of geometry. It comes into play in a lot of areas of physics, having to do with energy dispersing or the strength of forces as you get further away from objects, like the gravitational force, the electric force. So I think maybe I already said some of this stuff, but now that we've sort of calibrated our luminosity and period relationship for these Cepheids, we can make a graph like this, where we're plotting the period versus the actual luminosity of those stars. So this becomes very nice. You measure the period of some Cepheid and say it's like 10 days, right? Well, then track up to 10 days and right along that line that all these Cepheids are making, 10 days is maybe 1,000 times the luminosity of the sun. Or you go all the way out to like 50 or 60 days or so, period that long, 10,000 times the luminosity of the sun. So again, very powerful thing, just measuring the period of like how long it goes through this bright, dim, bright again, how long that takes, now directly can tell us the luminosity of those stars. And again, luminosity, along with how bright they appear to us, gives us distance. Also on that plot are some of the RR Lyra stars, Lyra stars. They all have a very similar period, and their luminosity actually is all very similar as well. Right? Which is another nice thing, because if you find one of those particular stars, then right away you pretty much know its luminosity. It's somewhere maybe like a little less than maybe 100 times the sun's luminosity. So I snuck in to the earlier calibration for these Cepheid variables, or variable stars sort of in general, a sort of calibration of the HR diagram. So brought back this HR diagram. To remind you, this is plotting temperature increasing from right to left along the bottom, and then luminosity vertically. We talked about this a good bit in the last lecture, but I'll remind you that that sort of line of stars that goes from the upper left to the bottom right is what we call the main sequence. Our sun is plotted on there, so remember it is like a G2 spectral class, right? A little less than 6,000 degrees Kelvin, and its luminosity on that chart is 1, right? Because that scale is luminosity of the sun. Our sun, 1 luminosity. There is a slight wrinkle in using the HR diagram to calculate luminosity, because the main sequence, that main diagonal line, are not the only stars on this diagram. There are these ones that are in the upper right. Those are the giants, if you remember, really, really big stars. And there's also these ones at the bottom left, right, the white dwarfs. So if we want to use the HR diagram to get luminosity of a star, right, just by looking at its temperature, we can just about get luminosity as long as we know that it's a main sequence, or it's one of these giants, or it's a dwarf. How do we tell that? Well, one way to do it is by the pressure of those stars. Right? If you remember back, you're talking about analyzing starlight, I think. I told you that we can get information about the pressure of the star's atmosphere by looking at its spectra, and particularly by looking at how like broad or fuzzy the spectral lines were. So in a giant star, and the really big stars, very, very big, very low pressure, low density, low pressure, and so those spectral lines end up being very sharp. As on the other end of the spectrum is the dwarfs. They're really, really small, very, very dense, high pressure, so their spectral lines end up being fairly blurred. And the main sequence is kind of in between there. So basically, by looking at the sharpness or blurriness of the spectral lines, we can place whether or not the star that we're looking at is a main sequence star, whether it's up here as one of the giants, or whether it's down there with the white dwarfs. In doing this, astronomers came up with another kind of class we call the luminosity class, which divides up the HR diagram into sort of the different sizes. And they're labeled Roman numerals 1 to 5. So here you go. These are the luminosity classes, and these are the kinds of stars that they correspond to. There are more like subcategories even too. Right here, the first category, 1, is broken up into A and B. So you have like the very brightest of the supergiants, and then 1B is like supergiants, but they're a little less bright. Then you kind of just go down in size to luminosity class 2 is really bright giants, 3 is just regular giants, and 4 subgiants, and 5s are main sequence stars. So if we look at the HR diagram, this one has sort of lines plotted where those luminosity classes fall. Right, so 1A, way up here, the highest luminosities that there are. So up here are like 10 to the 5th times brighter than our sun, 100,000 times brighter than our sun. Then to 1B, bit less, maybe like 10,000 times brighter than our sun. Then to class 2, class 3, class 4, class 5, right? In class 5, those are the main sequence stars. So like our sun now is spectral class G2, luminosity class 5, or B. So now, if we want to know what the luminosity of a star is, well, figure out what its spectral class is, right? How hot is it, its temperature, and then use information from its spectra to get the pressure to figure out what size it is, what luminosity class it is. Those two things together can place it on our HR diagram and say what its actual luminosity is. And then again, luminosity, along with apparent brightness, can tell us distance. This is a tough chapter, let's say that. Confusing sort of stuff. Hopefully if you have questions, you will ask. What I've been telling you about overall, well, is about measuring the distance to objects in space, particularly to like stars. But what we're getting at is something that's termed the cosmic distance ladder. So I've told you about like using radar, and then parallax, and also these pulsating variable stars, and the HR diagram, right? These are different portions of what we call this cosmic distance ladder, meaning that they work up to a certain distance, and then we kind of have to use another technique to really push much further. This image here is showing that radar ranging, or using radar to determine distances, is really only good within our solar system. Right? You want to get a bit further, then we start to use parallax, which gets us to sort of nearby stars. This technique with using the HR diagram, also known as main sequence fitting, right? Because you're plotting stuff on the main sequence or on the HR diagram overall to find its luminosity. That works pretty much within our galaxy. If you want to get to nearby galaxies, that's where you use things like Cepheids and other pulsating variable stars. If you want to get even further, then that is beyond what we've talked about in this lecture. I'm not sure, we might talk about them later when we talk about very large scale structure of the universe. And just like a regular ladder, right, you use one step in order to boost you up to the next one. So it's not like these techniques are split into very particular distance scales. You sort of leverage our knowledge from the radar ranging in order to help us better understand the distances that we're doing with parallax. And we also utilized our parallax measurements, distances to nearby stars, in order to give us more information that we could then leverage to look at further stars, right? So each rung on this ladder is sort of helping us get to it. Well, that's all for this lecture on cosmic distances, and I will see you later.